representation, which is not very useful. I will also need an eraser. Thank you very much. That's it. All right. So suppose instead we look at this other representation here. We have some functional relationship. Something like that. But we have some experimental units. So suppose we have John as one experimental unit, and we put John on the x-axis, and we have Mary on the y-axis. Typically, say the times that we sample, these things are fixed. We either use them as design, or we observe them. And what we are really interested in is the relationship between what happens when we change theta to y. So, well, first of all, I have observed some value of y for John. Blue, John is a male. So this is John observed. Y, John observed. And of course, I have some Mary, which is big. Y, Mary observed. So actually, in this plane, I have an observation point. Call it X, well, I don't know Y observed. And, well, suppose now I start playing with my theta. I give some theta value. I have some covariates, TU, whatever they are, for John. And this theta value has some prediction for John. Was this clear? I did something wrong.
Just mute the microphone.
All right. So with some yellow theta, I have this yellow prediction for John, and I had this yellow prediction for Mary. Okay. So I'm predicting here. Now, here is not there. Of course, with this theta, I make an error of some sort. I change my theta, and I change my prediction. I change my theta again, and I change my prediction. And now it should be perfectly clear that the set of values that my prediction takes is in general a one-dimensional, theta is one-dimensional surface in R2. Now, I can have many experimental units. I can have n experimental units. And in fact, my model need not be one-dimensional. I can have a few-dimensional model. And if I have a q-dimensional model with n observations, I have a q-dimensional surface in n-dimensional space. And the nice thing is that even if I'm in n-dimensional space, my whole observation is just one point. So what I'm trying to do is I'm trying to say, well, what is the value of theta that fits the point y observed best? And it's clearly this guy here, right? Whose distance from y0, y0 is minimal. Okay. Now, if by distance I'm in Euclidean space and I take the usual distance Euclidean measure, but I find OLS. So by the OLS criterion, this is my best prediction y hat, which is of course indexed by some best parameter value theta hat. So theta hat is the parameter value that brings me to the best point here. Fine. Now, why should I go to the trouble of using this representation instead of the usual representation? I'm trying to go quickly here because you don't have more time on that side. But if you have any questions, please stop me. I understand I'm not perfectly clear very often, so just stop me, no problem. Okay, suppose I have a linear model. Now I'm just drafting two of many possible dimensions. I am in Rn. I have a point, which is my observation. I will use X now for the observation system Y. Just now, if I have a linear model, the set of predictions is actually a linear subspace of Rn. It's a q-dimensional. It's not like Q, sorry. it's a Q-dimensional, let me call it M. The reason will be clear later. M is the predictional surface, which is a Q-dimensional surface in Rn. Well, how do I find the estimate? In this case, it's easy because I have a subspace. If I have a subspace, well, let's talk a little bit more mathematics. I have Rn, right? You will remember that Rn is endowed with a topology, which is the standard topology. And if I generate, say, algebra with the standard topology, I get the standard Borel-Sigma algebra, okay, in Rn. And in this Borel-Sigma algebra, I have the big measure, and this is the measured space, right? Fine. Okay, so in this case, I have more. The Rn is actually bound because it's complete, and there is a norm, and the norm is the usual norm. I equals 1 to n xi squared, actually, right? So this is the usual norm, and blah blah blah. So with this norm, this is a norm space, and this is norm space, and it's complete because I can read Cauchy sequences, da. And actually, I can introduce the obvious inner product, yeah. And this is the inner product, the canonical inner product compatible with the norm. So with this inner product and this Banach space, I get a Hilbert space. So this space is Hilbert. And if this space is Hilbert, then I can know that I have a projection because this guy is a Hilbert subspace of a Hilbert space, and I have Hilbert projections theorem. Okay, only that I have projection, but this projection called this x hat is unique, is the shortest distance from x or that I can have. Any point in here called this y is such that y minus x hat is orthogonal with respect to x0 minus x hat. Okay, I got all the nice properties. More useful. If I put myself in a statistician's frame, the statistician is going to tell me, but you see, this function that you have written, x equals f of some predictors u and some theta, okay, parameter theta, and this guy is q-dimensional. And this f for the moment is linear. So actually, x vector is u matrix theta, okay, theta vector, right? If this is true, then the following is true. Well, let's put ourselves in the nicest, easiest possible case. This is the real situation. I assume that this is true. But if this is true, there is a true theta, some theta star, such that there is a true x, a true state, right? But this true state, if this thing is true, must be somewhere here, say here. But I don't know where this guy is, right? Okay. But what can I? Well, I can say x observed is actually x true plus some error. Vector. And this error is actually made up of IID components. All, I'm putting myself in the nicest situation. All of them are normal 0 sigma squared. All right. Alan, I got kids, I got a wife, I got a mortgage, I need my salary, so I need to make assumptions in order to be able to do the computations. We'll do the computations here. So I'm making assumptions. If these assumptions hold, then this guy is a realization of this random variable, okay? And it's the sum of, actually, it's the square root of the sum of n IID components, which are normally distributed 0 sigma squared. Okay, great. So this guy, by the way, it's module divided by sigma squared. No, it's module squared divided by sigma squared. This guy is distributed to chi squared and degrees of freedom. Good. Now, what am I going to do? I'm going to do graph split. So I take my basis and I turn it around until I align it like this. And if I do this, I can re-express epsilon as the sum of n components, which are still n components, of course, which are still normal 0 sigma squared. Why? Because a rotation doesn't change the distribution of these epsilon I variables. So by the way, okay, fine. So now I can express these two patterns, all right? One aligned along the model and one perpendicular to the model. And the one aligned along the model is the sum of n components, which are distributed. No, wait a minute. Distributed how? This guy here has non-zero components only in this direction. In this other direction, all of them are 0 according to the basis, right? So this guy is actually the sum I equals 1 to q of some epsilon I distributed in the usual way. And this guy is actually the sum of q plus 1 to n epsilon i's. So in fact, this guy is the sum of n minus q squared. This guy's module is the square root of the sum of n minus q squared realizations of random variables which are distributed 0 sigma squared. And I said it correctly. So this guy here, which we will call E, the residual divided by sigma, is distributed by square, yes, but the n minus q degrees of freedom. Okay, why degrees of freedom? Because this is the freedom that remains. Now this guy here, we allow me to call this xi. Now xi, once again, is distributed chi squared, but this time with only q degrees of freedom. And if you have studied your statistics 101, you know that you can divide a q degrees of freedom chi squared by n minus q degrees of freedom chi squared, and you get a Fisher with q and n minus q degrees of freedom. And why do you care? You care because with that F Fisher, you can find a confidence interval for the size of xi. Now, xi, you have no idea what it is. You know the model, you know your observation, you know your estimate, your point estimate. You know the size of the residual, but not of the error. But what you really want to know is how far am I away from the true state of nature, which according to Fisher is this X star. And the point is, doing all these tricks allows you to compute a confidence interval on the size of your flow, not like we will say flow with an O, but flow with an A. It's an error, not a flux. Okay. Okay. There is no. Okay. First question. I gave a name to this thing. I couldn't find a name for it in my statistics textbooks. But if any of you knows how this goes, please tell me, and I will be happy to correct my ways. So that's the first question. Okay.
We call it parametric error because
it's not in the parameter; it's in the state.
It's not in the parameter; it's the X. Yeah, so it's not the parameter. It's the prediction.
Prediction.
We call it prediction. If this affects, so is the prediction X star is
first question answer. Flow equals prediction error.
Yeah.
Great, thank you very much. All right. Great. I mean, life can be easier. We have just used Pythagoras' theorem and we have found a lot of things. However, not every time we have a linear model. So let's assume that now the relationship is nonlinear. And if the relationship is nonlinear, and I have some observation, then what do? Relationship is nonlinear. The prediction surface is nonlinear. It's not the subspace of the Hilbert space. It's not even convex. I can take a point here and a point here, and the whole segment is outside of the surface. It's not convex. I have no Hilbert theorem. I have no uniqueness. I have nothing. So what I say is, if I were an engineer, no disrespect to Gaetano, of course, I would say, oh, right, yes, but come on. You limit yourself to some interval where you have some point which is locally closest. You find it numerically. And then you say, all right, so this is easy, okay? This is X hat is easy because I can just use my mean search or whatever you use and then find the local minimum of the thing. But then how do you work with confidence intervals? Because once again, you want to have some size estimate of the prediction error, right? Okay. What you do is typically you linearize, compute your Jacobian, and you say, in this case, it's actually a little bit skewed. So, yes. Okay, and if this is the Jacobian, then this is perpendicular, and you move your computations as if this were your model. It is not, but you use this instead of that. Can you do it? Yes, you can. And of course, the asymptotic confidence regions that you compute are not exact anymore. They are approximate. How well approximate are they? Well, it depends on the curvature at X hat. If the curvature is excessive, you are trying to linearize something. This, it's junk. If your thing is like this, you feel much better. And we have published in the past criteria whereby you can decide whether you are sufficiently linear or sufficiently not to non-linear that you can do this thing with a reasonable error. Okay, enough statistics. No more. Now, so we're doing model, right? And once again, please, I'm a biological modeler, so I do biological exams, stupid biological exams. Suppose I want to predict, okay, suppose I have the following situation, just to make things palatable. I am building a set of elevators for a skyscraper. But of course, if I load too many people on the elevator breaks and falls down. So no. But now, these days of artificial intelligence, I can put a camera in front of the entrance of the building, count how many people can be in, and forecast their weight based on their height, say, okay? And then, of course, if I have already 32 people came into the building and have to get into the elevator, I will stop. Yeah, I'll close the doors. So what I need is some kind of model, weight as a function of height. This is the stupidest model I could think of. And my first question is, what is age? Lady, sixth row with a ponytail and glasses. What is age? Pasquale Palumbo's doctoral student. What is age? Hey, come on, Jeff. Age is a height. It's a height, right? Whose height?
I can assume it's a random variable with some.
Yes, we are lucky that we have Professor Buzano with us. Okay, Because it cannot be my height. It cannot be my height because in this case, K, this will be my height, this will be my weight, and K will have some value. And if we take Luigi, this would be his height, and this would be his weight, and his K would probably be different from mine. So this is not a relationship between the height and the weight of some people. It cannot be an arithmetic relationship. Cannot be, okay? Because if it were, I would assume that all of us would share the same perfect arithmetic relationship between height and weight. No, no, no. And once again, we are talking, we haven't observed anything yet. But what we are saying is, as Fabrizio suggested, that height is some random variable that I could observe. You know, I go to the skyscraper and I measure 30 people, then I have 30 observations of height. So I would have 30 realizations of this random variable. All right? Okay, so this is random variable. Please.
I'm assuming you also have measurement errors, so maybe you don't have some age, you some age maximum.
We assume that there is variability. Whether you are in your wisdom, you want to attribute it to measurement error, to heterogeneity in the individuals, to whatever. It's up to you.
And you put everything in.
For the moment. That's good. Okay, so lady sixth row, ponytail in glasses. What is that mean? Wait. Is it a random variable? Yes or no? It's a yes or no question. Yes, it is a random variable. I agree. It's a random variable. What does it represent? Of whom?
Maybe the weight that will like if like the observation, but the kind of related weight people are coming into the
Yes. Very smart. Yes. In fact, this weight, which is a random variable, I agree, is not the random variable whose realizations I might observe if I were to measure 30 people. No. The fact that this is a random variable stems from the fact, actually from Hildinkin lemma, from the fact that this is a function of this guy, and this is a random variable. So since this is a random variable, then this is a random variable. But this is not the random variable of the weights of the people I observe. So let's assume that we observe another random, that we could observe another random variable, which is and this would be the random variable whose realizations I might observe if I were to measure people. Now, a model is something like this that makes this random variable, and this random variable, if the model is good, ought to be near this random variable here. As you said, thank you, this is a forecast or predicted or prediction or whatever you want to call it, random variable, and this has to be near this if the model is pretty good.
So here, so you assume that K here is deterministic. So in the model, K is deterministic.
In the model, yeah.
Because you were saying before that in reality, K they can change between myself and yourself.
If I assume, as I
should you describe with a model where K is deterministic.
Yes.
That's
yes, this is the setup. We can discuss the setup. Actually, I find myself in the position of describing things from Fisheerian point of view, which I dislike intensely. I honestly believe that only a Bayesian approach is tenable, but that's a different story. Okay, so for the moment, yeah, K is a parameter, is a deterministic parameter whose value we want. Okay. Okay. We said near. Near. What does it mean? Near. Sorry. What does near mean? Don't do this. I understand that you understand the question. Yes, I'm talking. Yeah. All right, I'll tell you.
I mean,
I guess somebody else. I know that to pick one and the same. What does near mean? The question is, what does it?
You said that it's random variable with distribution.
Yes.
Near be in a certain distance, like the distance we're going to define.
Yes, but in order to have a distance, what do I need to have?
Space.
In order to have a distance, d x, y of some x and some y is what? Do you agree? Something like this? Oh, all right. This is x minus y. I'll rewrite it. I'll rewrite it. I get carried away. Huh? Answer? Do you agree that this is the definition of distance? It could be. Right? It makes sense. What is this? What is this?
It's a normal.
It's a norm. Ah, so we need a norm. Yeah, so we need a normed space. All right. Okay. Help me. What's the definition of a norm? Now, a norm is a function from whatever to R plus, such that triangular inequality. I will not write everything. And then the second thing is the thing makes the normal 0 is 0 and separates points. This is important. The norm is such a function. So suppose a norm is indicated by this, then this is 0 implies x is 0 in whatever space you have. Do you agree? Do you agree that on random variables we don't have a norm? All right. Well, we have to define some function. I should say here. What can I define as a norm? The expectation, say. Okay, I'm just going to square blah blah. Okay, so the expectation of square is something like this. Is over whatever it is, x squared dp. Okay, so now I have probability space. Huh? I need to have probability space in order to have random variables, right? Okay, so I have a probability space and I have probability measure, and so I define this guy to be the norm, okay, of x. This is the norm of x. And my contention is that this guy does not satisfy axiom number 3. Why? Because I can have x and y such that they are equal almost everywhere. They are equal p almost everywhere. And this means that the integral over whatever you want to have, x minus y, absolute or whatever you want, dp is 0. All right? But x is not y. All right. So we have to introduce an equivalence relationship, which is the equivalence relationship p almost equal p almost everything. And then we have to quotient the space, which is actually L2 in this case. And we have to quotient it by this relationship p almost everywhere. And so if we want to do things correctly, we don't have to talk about random variables. We have to talk about equivalence classes of random variables, which are represented by some representative member of the equivalence class, and blah, blah, blah. Okay, fine. On this space, this guy is a norm. So now we have a normed space. Also, you pick your favorite criterion for conversions in random variables. There are several. You can show that this space is valid. And then always, with a little abuse of notation, we say that when we talk about random variables, we really talk about equivalence classes of random variables. And so we say that x, y, say, is this, okay? So now we have an inner product. The inner product is compatible with the norm. And so we have the Hilbert space. We have the Hilbert space, and we also assume that this guy is finite. So now we have a space, which is H, which is the space of random variables, this class is of, with finite variance, with this norm, and this is the product. And this is our setup. So now we can talk about making a model. Because now we have the ingredients. We have a space. Allow me to just, this makes no sense. This is H. And in H, I have some random variable. Remember, we had an objective random variable, and we had a predicted or prediction or whatever random variable, which is a function, in this case, a linear function of another random variable. Okay. And in this space, we have W. What we have WO. We have some W. But of course, this W is a function of K. Change K, change the forecast. So, look. In this case, we have a subspace, but we have already said we have a Hilbert space. Now we have a subspace, and it's a linear subspace. So it inherits everything. It inherits a Hilbert space itself. It inherits the topology by the subset topology. It inherits there is a sigma object that can be limited to that. You got everything. Since you got everything, you get Hilbert's projection theory. So you get your W, which in this case is a random variable. A random variable in this blah, 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 blah. Okay, fine. Everything works beautifully. Now suppose, to make things complicated, we're 2/3 or 3/4 along the way, so you don't have to worry too much. Suppose we have a nonlinear model. Now, a model, the way we have defined it, a model is just an operator on random variables, which I will remind you are measurable functions from omega to R, say, or R cubed, in this case. No, sorry, Rn, measurable. So in fact, I have to have omega, and I have to have some sigma algebra here, which I do have. So this is a measurable space. And here I have the usual story. I have Rn and I have Rn. Fine. So this is measurable in this sense. Okay. And this is measurable also because by do thinking, I have omega, and I have X, and I have Rn, and then I must have some function, whatever, f of whatever it is, and this has to be Borel measurable. And if this is Borel measurable, then by thinking this is f Borel measurable. So this thing, which is f after x, which is your W in this case, okay, this is also measurable. And this is measurable, then this is a random variable. So we are happy. Fine. So now you're in this situation, and you do the same thing as before. You have some WO, you don't have subspace, so you don't have Hilbert, you don't have the projection, and you say, well, let's compute the tangent space. Now, how do you compute the tangent space to do the computations there? Actually, you don't need to do computations. This is just anatomy if you want. How do you compute the tangent space? Well, in general, if your model, so if your operator is sufficiently regular, this animal here is sufficiently regular, which means that it's a Q-dimensional, now it's not a prediction surface anymore. It's a Q-dimensional manifold. And we go back to it. And if it is a Q-dimensional manifold, then you have charts. And charts are for any point P on the manifold, you have some open U, okay? And you have a chart map, thank you, Fabrizio, going a chart map, call it mu, just with a name, that goes from U to RQ. And if you can cover the whole manifold with these charts, then you have a manifold, okay? You have a topological manifold. In fact, here we require to have a differentiable manifold, which means you have an atlas of maps, you make decisions, you throw away everything you don't like, which means you throw away all charts such that the composition of a chart with the inverse of another chart is not differentiable. All of those you throw away, which means that your atlas is composed of all those maps mu such that mu composed ni inverse is differentiable. C whatever you want. C infinity, smooth. Okay, go on a smooth atlas. Actually, it's not too much of a trouble with that. Okay, if you have this, then any map, any chart map you have will obey this requirement. But this is an artificial requirement that you choose yourself, that you impose yourself. Okay, assuming we have such a manifold, such an atlas, then we have differentiable manifold. Now we want to build a tangent space. How do we do that? Well, standard construction in differential geometry. I know that you're all brilliant mathematicians, but maybe if I make an example, I can make things clear. Anybody skis here? We're in Turin. There's Courmayeur not too far away. Do you ski?
I used to.
You use no, somebody who skis. Nobody skis. Fabrizio. All right, so Fabrizio is skiing. Was skiing. So assume that Fabrizio is skiing. And Fabrizio is very happy skiing because, you know, the Plateau Rosa, whatever it is, okay? And he is, you know, nicely with his shoulders towards the back and everything. And he is following a path, right? He's skiing along the path at some speed because valiant, sporty fellow, so the speed might be, okay, fine. So some speed, which means if you allow me that he is following, if the surface of the hill he's skiing on is your manifold, he is following some curve, where curve here doesn't mean the path, it means the path and the time. Some curve from some interval in R time to the manifold, okay? So he's following this thing, and maybe he's curving, it's nice. And he is actually working on his tan, right? And he wants to know how his tan is going to benefit depending on the curve that he is doing and the speed at which he is doing it. How does he do this? Well, he says, I have the meteorological service tell me what the solar intensity is at any point on the manifold. So now I have the function f, which is solar intensity manifold to R with some number, okay? And what he wants to know is if I ski in the direction that I am at a point, in an instant, and I'm skiing at some speed along this path at this instant, at this point. And at this point, I have some gradient of solar intensity. What he wants is a directional derivative f after gamma. And f after gamma is easy to compute because f is m to r, but gamma is r to m. So f after gamma this is gamma, this is f. Gamma goes from R to M, F goes from M to R, and this is F after gamma, which goes from R to R. This is high school analysis. Easy. I can do an easy derivative here. I couldn't do a derivative on the manifold. I could not. The manifold does not have a vector space structure. It has a topology. But it doesn't have a vector space structure. I cannot compute the derivative of the manifold because there is no difference. Okay, right. Okay, but I can compute the derivative here. Now, this is if he wanted to work on his tan. But suppose he is worried that the snow is going to be it's snowing too much and he has to stop skiing. Well, then he doesn't want solar intensity. He wants snowfall at each point. But suppose he doesn't want to have snowfall, and he wants wind speed, and wind speed is G. Okay. Okay, where do I want to go? I want to go here. I want to say, look, this guy here is a generic differential operator taking the point, and of course, at some lambda where I am, taking the geometry of the path, and I can apply it to any function I want in order to have the directional derivative along that path at that point of that function that I chose. Okay, I will not make things too complicated, I hope. But the point is, I can use the same construction here. And if I use the same construction here, I can build a directional derivative with respect to some generic function. But the point is, I yet have to do one step forward. I have a q-dimensional manifold. So it stands to reason that my tangent space, and here there is, I'm slightly lying to you, but I will make things more precise in a moment. This tangent space is also q-dimensional. So it is spanned by some basis. Okay. How do I compute the basis? Well, okay. I compute the basis if I have a chart, at least a local chart. And it's going to be a basis dependent on the chart. Do I have a chart? And now we're talking totally abstract statistical manifold. All right. And I have a random variable here. Do I have a chart? Of course I do. I have a chart. You see, in general, this animal here is W as a function of some theta. And this theta, allow me to call it M, the model function, okay? The model operator of theta and possibly other variables, okay? Call them U, H, whatever they are, okay? I have a model. The model is such that if I plug in a theta parameter comes from RQ, then I get a random variable. And all of these random variables, the set of all possible random values I can compute here is this guy here. So if I am at this point, I know that I have a map, which is the chart map, which is the model chart map, M, that goes from M to RQ. But I was in an atlas. If you remember the atlas, it was a very nice atlas. It was actually a smooth atlas. It had all kinds of charts in it that were not only continuous and whose inverse was continuous. This is guaranteed for any topological manifold, but charts such that they are differentiable and the composition chart is differentiable. So I just need to take the inverse. And this inverse, going from RQ to the manifold, is a chart. Sorry. Yeah, oh yeah. No, sorry, I made a mistake. I made a mistake. Allow me. I have a model. So the model map maps RQ to the manifold. So this is M. And the inverse of the model is my chart. Sorry, I made a mistake. So I am guaranteed, in this case, to have a chart map, which is global. It covers the entire manifold. Why? Well, because by the model, I could plug any theta from RQ, and I would get some member of this set, some element in this set. So it's onto. And according to this here chart map, I can build and you can compute a basis for the tangent space. Okay, now I'll correct myself when I said I was lying to you slightly. This is not a subspace. This is a vector space of differential operators, and it is actually spanned with the elements that I built from here. But it's not a subspace of H. It's an affine subspace of H because it's shifted to whatever it is that I need to shift it to. So this affine subspace, well, it can be easily shown that Hilbert's projection theorem also applies to affine space. So in fact, even if I have an affine, not a real subspace, and I have W O here, I still have on this affine space a unique projection, which is locally, now I'm only talking locally, which is locally optimal, shortest distance, such that it's perpendicular to any element of the tangent of the affine tangent space, etc., etc. Fine. Okay, now we have enjoyed our mathematical pleasure doing this now. And the question now is, what is the relationship between this stuff and this stuff? And if I were to ask any engineer friend of mine, they would say it's obvious. It's obvious. I mean, here you're talking random variables. Yeah, Andrea, you're making things more complicated than they need be. But that's that random variables. You observe go here. So there should be a mathematical relationship between these guys and these guys, right? And the question is, what is it? And of course, I think I have the answer. Gentlemen, fourth row glasses, and yeah, you. What is your height?
My height?
Yeah.
1.65.
Your height.
188.
Your height.
87.
What? Will not embarrass you. Okay, so height is a random variable. Height is a random variable. And I have realizations of this random variables, right? Okay, sure. Now, sorry, Luigi, what measure should you have? 42, 43, 39, whatever, okay? So should measure is another random variable, okay? Age is another random variable. So I have, by definition, I have random variables. I have X, Y, W, H, whatever. They're all random variables defined on some sample space. And sample space here is you guys. So I pick Fabrizio, that's a realization, that's a sample or realization of the within the sample space. And from this realization, I map some random variable. So X goes from omega to R, and Y goes, this is height, and this is not this height. This goes from etc., etc., etc. Okay, they all do the same thing. But I can go back to my friend with the glasses and the bandana, however it's called, lanyard, yes, with the lanyard. Okay? And I can ask you, what is your shoe size?
41.
What is your height?
1.65.
What's your age?
My age? 25.
Okay. Whoa. Then, now I'm doing a different thing. I have picked a point. What is your name?
Yeah.
I have picked a point omega, which is Gabriele. And from this omega, I have a number of values of different random variables. So in fact, I could think that omega cross H being the space of all possible random variables. This is my domain. I can fix omega, Gabriele, I can fix H, something in H, height. Gabriele and height come to 175 or whatever it is. Okay. But if I take the same Gabriele and I fix a different random variable, then I have a different number. In fact, this representation of the random variable just tells me the random variables are the marginal map from this Cartesian product set onto R when I fix H. But Gabriele, our friend, is another marginal map from the same Cartesian product set, where instead of fixing the random variable, I fix omega. Now I fix omega, which is Gabriele, and depending on Gabriele, different random variables give me different numbers. And now you see that if I fix the realization, if I fix omega, everything in here gives me a number there. Because if I have the omega, that observation comes to whatever I observe here. And given little omega, my x hat becomes my x hat here, etc., etc., etc. So even if Gabriele doesn't know it, Gabriele is a map mapping the set of random variables onto the set of the realizations of such random variables, whatever they are. And this is the connection between theory and computation. Okay, to sum it up, a model is not, it's obviously wrong. A model is an operator on the space of random variables, or finite variance random variables, delivering a prediction random variable, okay, depending on something, including parameters. A model is good if the predicted random variable is close in the metric of this Hilbert space to the objective random variable, which is the weight of real people. The construction that we make here includes both simple things like linear models and via differential geometry, suitable tangent spaces. I didn't give you many details, but yeah, so on. And there is a relationship between here and there, and the relationship is the map given by the realization. The realization is a map from the space of random variables to the space of computations. Once again, I didn't find this stuff written in any book, but if you can point me to where it's written, I'd be perfectly happy to go and study it. Thank you very much.
So, of course, I think you have many questions. So, I can open them. Yeah.
Okay, you start and finish by saying that you were not able to find what you are stating today in the literature, right?
Right.
So I have some difficulties getting what is exactly the point about what you are looking to find, because most of the stuff that you...
This is all known. Okay, no problem. That there exists a space of random variables is also well known.
Yes.
In fact,
Also Hilbert space.
but yeah, it's it. In fact, hold on, okay, give me 2 minutes, 1 minute. One of the standard applications here is conditional expectation. In conditional expectation, what you do is you take a subsigma algebra of this space which I erased. Okay, let me rewrite it. So you have a general sample space with general sigma algebra with a measure, and instead you take a subsigma algebra which is rougher than this F. And what you can show, it's relatively easy, is that the set of random variables which are G measurable but not F measurable is a proper subset of this H, called this subset H sub G. This subset is a linear space, is a Hilbert space in its own right, and you have the Hilbert projection theorem, and everything works. And in fact, the projection is the conditional expectation. Fine. So all of this stuff is well written, but it's not what I was talking about. I'm not talking about a linear subspace induced by a sub-sigma algebra. I was talking about a non-linear, possibly non-linear manifold, not a subspace, induced by the model structure. So that's a different story. And I did not find that written. The reason, sorry.
I don't know, maybe I missed something, but it seems to me that in the case of the nonlinear manifold, what you are talking about is local linearization. So it's a matter of computing the Jacobian of the function and then applying the projection.
Here. The Jacobian you computed here.
Yeah, but when you pick a realization of the random variable, you are there.
Certainly, certainly,
Stuff.
certainly so. So let's fix idea. Jacobian is around here. What is the Jacobian there? The image of. It must be the image of some tangent space or affine subspace or whatever it is. And the question is, how do you build that? It's not written that, I have not found it written how you actually build in this situation the subspace or the tangent space that actually gets mapped to the Jacobian here. Once you do this and you accept the fact that your realization is the map, then you find the Jacobian. It's fine. But this anatomy, if you will, I have not found.
So it's more
there's one
of formulation than
yes.
the solution.
Oh, certainly, certainly. The solution, we have been using this stuff for 200 years. There is another example. You know information geometry, probably you probably heard about that. And that in information geometry, we are talking about manifolds of probability distributions. And there is a link between this guy here and information geometry in the sense that each random variable on the same probability space, each random variable induces a probability distribution, and each probability distribution can be induced by at least one random variable. If you do the usual quotient space quotient trick, then there is a bionical correspondence. But again, the two spaces are not the same. In information geometry, you deal with the space of the probability distribution, and you're typically interested in situations like convergence or probability distributions in the limit to asymptotic limits of things, families which are flat in a kind of Riemann sense or this kind of stuff. Here, we are concerning the model itself, the model, not the distribution. The random variable as the product of the model. So yes, there is a relationship. No, they're not the same thing. This is what I understand, but I'm perfectly happy to be corrected.
Oh, I see your point. The solution at the end is the same that we have been using. This is an interpretation of what we have been doing.
If you will. Yes.
I have another, if I can, very, very fast. One is about the fact that it seems to me that you always consider static relation. When you say that X,
because they come from dynamical system.
Because my point is that you, at some point, you say that X equal X of
time
theta plus epsilon, where epsilon is IID. So if the system is dynamic, you cannot assume that the epsilon is IID.
Three answers. I'm trying to make it quick. First, without loss of generality, we can assume a static system, if you will, because if I have a dynamical system, a system of differential equations, and tomorrow we'll see differential equations of different kinds. Which say, well, you start from here, possibly there, you apply your differential equation, and you numerically compute something. So I can assume that you have computed the solution, and after you compute the solution and you decide to sample at these time points, then this, and that are the dimensions of my embedding space Rn. So I have in this case 1, 2, 3, 4, 5 dimensional space, and the point is the point represented by these values.
Yeah, but you compute the solution if you know the model.
Yes. Yes. What's wrong?
No, the point is that you say,
Problem.
mm,
Is there any problem? I compute the solution given theta. This is theta what? And we had said in the beginning, I might have,
So this is what we call
Yeah.
a multi-step prediction.
okay, theta yellow and theta white. Now I have a five-dimensional space. This is my theta white. This is my theta yellow. And in fact, as I change theta, I trace a manifold in this Rn space.
But I think I see this.
my point is that once you collect your data, your observation X,
Yes.
X at time T depend on X at time T minus one,
Absolutely.
and so on. So it means that if you say that X observation, it is X function of theta plus epsilon. Okay, so if there is this kind of dynamical dependency, epsilon is no more IID. That's my point. That's for sure.
Okay. So one thing at a time. First, the fact that epsilon is not IID, for instance, the epsilon is the typical case is weighted least squares, where epsilon is actually depending on the size of the prediction. It can be reduced to the OLS case by a suitable change of space. So that is not a problem. What you're saying is, suppose I have, suppose, let's put ourselves in the worst possible situation. I have a non-Markovian system. Non-Markovian. My next observation depends on all the previous observations. That doesn't even depend on the previous observation number one. It depends on the whole past. So what's the problem? Once again, if you have a deterministic system and you're observing with error, then you fall in this case. If you have a stochastic system where the state depends on the error that you make on the previous point, then you are not in this case anymore, and I have to study more to try and express it. So this now works for deterministic models, where your observation error or your heterogeneity error or whatever does not depend on previous states.
And the last one, when you have a strong statement, because you say, for me, a model, it is an operator that maps a random variable into another.
Yes.
But if you think, I don't know, any physical system where you have that, the model of the system described.
I'm a mathematician, what can I say?
No.
No.
The point is that a model, I don't know, if you are modeling the glucose insulin dynamics, for example.
Tomorrow.
Okay. Maybe your task or my task from the control point of view is to build a model where from the injected insulin to the glucose concentration, for example.
Yeah.
Injected insulin is not a random variable. It's a deterministic quantity.
Yes.
And so what's the point? The model I'm looking for is not an operator between.
Prevents me from considering in the ingredients of my operator zero variance random variables. I can do it.
Sure.
Okay. Now, if you say, I can think of a model like there was this very famous 1949 econometric model. This guy, I don't remember the name. He built a whole hydraulic system with pipes and water and valves and taps, and he would open the tap of family spending and the level of the water in funding reserve would go up. Yeah, that's a model too. Sure, it's a physical model, but I'm not talking about that. I'm confining myself to mathematical models.
Yeah, it is also my field. Now, the point is that if I build a mathematical model of something, I mean, agree with you that you can
make an example. Give me an example. Just make an example.
The insulin glucose dynamics.
Now I have insulin glucose dynamics. We want to think glucose, right? Right. Yes. Okay. Let me throw down just the differential equation, just to make something. Okay. So dGdt ordinary differential equation of the problem. And I have some hepatic glucose output, I will call it Kg, and then I have, let's make it really simple, minus K O G I G, with G at time 0 equals G0. Do you agree?
What is I? Is
Insulin. Okay, you agree with that?
yes.
Okay, do you agree we solve it numerically? We can. This is actually can even be solved explicitly, and but better people than me can do this. I am sure that Ouija can do this. Yeah, it's but the point is, I can have an explicit solution of this system, or even a numerical solution of this system, and so I would have over time, I would have some input function of insulin, and correspondingly, starting from the value G was 0, I would have some I, whatever.
Yeah, by fixing the value of the parameter.
By fixing the value of the parameter. Now, I change the parameter, and in this case, theta is set Kg, K, OGI. Okay, it's a two-dimensional parameter. By fixing this, with the same I get a different G.
Yeah, there is nothing random there.
Sorry,
There is nothing random there.
there's nothing.
Random.
No, we said this before. This is the deterministic model. This is a deterministic model. Okay. Now I can observe with air. So now suppose I observe here, 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 and here, just to make an example. Now here I observe this glucose, and here I observe this glucose, and here I observe this glucose, and suppose the insulin is perfectly known. Then now I have R4, I have a four-dimensional space in which each dimension is the value of glucose at a time point, and where the yellow curve is a point in four dimension given by these four coordinates. And the white curve is another point in four dimension given by these four coordinates. So I'm reducing the usual representation to the case space representation. Didn't say that, but that's called the case space. Okay. And in case space, I can do the geometry.
Yeah, but I'm still not getting the point of defining the model as mapping between random values.
Okay. Do you agree that you do the computations here? You are in case space, you have numbers, you use R or MATLAB or whatever you want. Okay.
This was.
I am perfectly, yeah, whatever. I'm perfectly happy that you do that. I am not criticizing it. I am just trying to understand what it is when you and I, before you observe any numbers, sit down at the table and we start talking about modeling. What are we talking about? This is what we were trying to do with the lady with the planetarium. Before we have any numbers, we are talking random variables in general, and we are talking about relationships between random variables in general. And if I produce a random variable which needs to be in this Hilbert space, finite variance, blah, 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 because I need a norm and the distance of that. If I reason on that and I want to produce one which is near my objective, I need an operator that takes something and produces a random variable. That's all. That's a model.
Could be something else, not necessarily a random variable. Could be
Exactly.
a scalar. Could be.
Wait.
Wait.
No. Allow me to address this question. I'm perfectly happy with the scalar random variable. I'm not happy with the scalar which is fixed, because if it is fixed, what is your relationship? What is the relationship between?
No, my point is the following: a collection of fixed value is not a random value. That's
I debate that. A collection of fixed point is a two-dimensional zero variance random variable. I do not exclude zero variance random variables. The point is that they exist in the same space. They're not very useful. But they exist. They are there. You mean it's,
We, as a control guys, we have some variables that we control, and thinking of them as under variable makes us
nervous.
because you have an input.
No, but my point is not this. It seems that this is some additional structure that you add, and I cannot grasp what you gain by saying that a collection of fixed numbers is a random variable. Where is the randomness inside? That's the point.
Okay.
So the fact that when you open the elevator and you can say people of different height coming in is not making the height of a guy a random variable. That's
Oh, yes, it is. Oh, yes, it is. In the sorry. Okay. Allow me to answer your first question first. Why do we do this? So why do we add this superstructure? And the reason is essentially anatomy. As Fabrizio was so nice as to mention, I actually come from a medical school. So you do anatomy first, and you do physiology after, and you do pathology after, and you do clinics after. In order to understand what you're doing with the clinics, you have to have the physiology, the pathology, and you have to have the anatomy. This thing is the anatomy of how models exist. It doesn't have any practical application. I understand that. Okay. But this is essentially the framework in which this thing operates, if I am correct. And I may not be correct. I may be wrong. But if I'm not wrong, this is the framework.
Yeah. Would like to add another layer of philosophy on this.
Please.
Your randomness arises from the fact that you are considering multiple people, and your realization is speaking at specific people.
Yes.
Okay, so I consider.
I disagree with the term multiple. It could be one person.
Okay, so in that case, the random variable
Is a scalar.
Yeah, you can also have one value, and it's pointless to consider a random variable.
No, it's not pointless. Wait, no, wait a minute.
If there is a,
Wait a minute. I want to give as many euros to one of you as you are told. But I have to pick one of you, and my eyes are closed. Okay. Now, if I pick one of you, that's a random variable. I don't know if I have to pay out 175 euro, 168 euro, 187 euro. I don't know. That's a random variable. The moment I consider things and I have my eyes closed and I start doing modeling, whether I use a scalar, objective, target variable, or vector value, it's the same thing. It's a random variable.
Yeah, so it depends on what to define what is a random variable. So this is
No. Okay. I actually,
something that you don't know or chance.
please, may I answer? I would like to have the opportunity to answer this question.
So randomness in nature, well, you find it in quantum physics, maybe, but so if
May I answer? Okay. I think I have what for me is a very convincing answer. Probability, whether it exists or not, I don't know. So randomness, I don't know. I don't know. Okay. In fact, if I had a soccer field and I knew that 1 square meter of soccer field takes 1 liter of water per day to be watered, and I knew that the soccer field is 50 meters by 100 meters, and I would compute 5,000 liters watering for that soccer field. Am I sure? The answer is no, because what happens is this is reality and this is mathematics. So in the case of the soccer field, what I have is I have a soccer field, all right? And then I say, it looks like a Euclidean rectangle. So I make an assumption. I go to the rectangle in Euclid geometry, I compute area in Euclid geometry, and then I go back to reality. But this assumption and this conclusion are not mathematics. Okay, this is your risk or my risk. Same thing with probability. Pascal discussed about the probability of picking a card out of a pack of equiprobable cards. But then the definition was
If you say every probable, you already say that.
exactly. So it doesn't work. Fisher said, if I observe the same thing a million zillion trillion times, then the relative frequency approximates the probability. What is the probability they bore you? I should have to deliver this lecture a billion zillion trillion times, and you don't want to do that. Okay, so Fisher is not tenable. Definetti was okay. So what happens is the following: a guy I really love, takes probability math, takes the measure theory, and says, look, measure theory is a purely mathematical topic. I will twist it a little bit, change the names. Measurable function becomes random variable. Measurable set becomes event, and this kind of things. But it's actually measure theory, no change. And I give it to you as a theory of probability. You want to accept it? Good. You don't want to accept it? Fine. It's your stuff. Now, Pascal works with Kolmogorov, and Fisher works with Kolmogorov, and Definetti works with Kolmogorov, and I work with Kolmogorov. It's a theory. There is no reality behind it. I totally agree with you. The random variable is a measurable map from omega and its sigma algebra to Rn and the Borel sigma. That's it.
Yeah, but you apply it to reality. That's the point.
You apply it. I'm a mathematician. I only do the computations.
Yeah.
We do that.
Yes. From an engineering, since we are engineers, I
I'm
would
not.
like to step
I'm not.
down and
In my research group, I am in the minority. There are 3 engineers, one statistician, myself. So I know how this to do that.
yeah, my problem as an engineer is that once you accept all of this, you say that you have a different realization according to different people. And then you compute your parameters according to the fact that you are taking your measurement with this paradigm. Then you will end up with parameters that are somehow considering all the people.
I don't understand.
But if I build the swing controller using
You understand the question? Yeah. No, sorry.
No,
I did not understand it. I did not understand the question. Could you please repeat?
is that you are performing the estimation out of this paradigm, you are performing the estimation of the parameters using all data from all people. I assume.
No,
I am doing no estimate.
that's the point, that he is picking the specific observation, right? When you say X, O,
All right.
and you use X,
The specific observation is here. Okay. Yeah. Go ahead.
okay, that you come back to the specific observation when you consider a singular realization, right?
No. No. XO may be a vector value
Okay.
realization.
In the sense.
It is the realization of a vector value when the variable. Nobody said XO here.
Okay, this is clear. So the point is that is not picking. I mean, your point is that you guess that he's looking for a general model, not for a specific system, right?
Does your model consider only one person? Or
No.
okay, so
It could. It depends on you. The design depends on you. I'm not even suggesting a model. I am just trying to say what a model is.
His model is a mathematical mapping between different models.
Yes, sir. Yes, sir.
Without saying that this that something is random in there. That's my point.
No, okay. You can say it's.
No. What I'm saying is a model, yes, it's a mapping that maps something into something else, but the something into which it maps is a random variable. So what I'm saying is a model is an operator on its Cartesian product of RQ and H, possibly giving as values an element of H, a random variable. That's a model in my description. Now, it may be wrong, but this is what I'm saying.
Okay, do the last question because otherwise. then we can continue the discussion. So at the given point, I'd ask you if K was deterministic. But then when I went back thinking there, at the end, you were constructing confident region on K. So at the given point, K becomes.
I am surprised that you ask such a naive question, if I may.
Yeah.
From a Fisherian point of view. Now, if you want to talk Bayesian, that's a different story. My confidence region is not on the state, but it's on the statement that I make if I say that my prediction is within so much of the state.
Okay, max is not.
So the state is fixed, unknown. According to Fisherians, it's unknown but true, and therefore has no probability to it. What it has probability, the confidence interval, is on my statement saying that my prediction falls within so much of the true state.
And okay, we have several questions, but we can. So one comment is that usually there's no true state in the sense that your model is not good enough to capture reality. So usually a model is an approximation. So when you use this model, it is an approximation. So there is no true X.
I totally agree philosophically, but if we had to assume this, you and I would be without a salary. Because any computations that we do assume something. So if as a statistician I tell you that the average age in this class is between 35 and 55, okay, whatever, okay. I am assuming a model, and if I did not assume that this model is true, I would not be able to make this statement.
No, I mean, my philosophy is that the model that we get is the best that you could obtain from the family of models defined by.
I disagree. The functional form of the model depends on the modeler. Depends on you. It's you who decides whether you want to use a linear model or not. When you do the computations, you assume the model you have postulated is true, and under that assumption, you estimate the best possible parameter value. Under that assumption.
No. Our philosophy is different, but because our philosophy is that is the outcome that we were. I'm happy with a linear model. I know that the word is not linear. I'm happy with a linear model. What is the best linear model that I can take? I know that my reality is not linear, but I'm using the Ohm's law, V equal Ri. It is not true because it depends on temperature, it depends on humidity, it depends on a lot of things. But for what I'm concerned, this is enough for me when I want to design my brain. And so I get the best data of R.
So you are estimating the diameter of your copper wire based upon the linear Ohm's law.
Yeah.
Fine. I agree that the value of the diameter of the copper wire you find is optimal, assuming linear Ohm's law.
Yeah, sure. Excellent.
We agree.
But the true model is not that.
But if you don't assume that,
Okay, assuming, okay, it's the word assumption that we are using different, but we are doing the same thing.
yeah.
I think we can. I mean, it was very. We can have more.